Welcome back. This is module 3 in our programming basics playlist. So far, we have covered what programming actually is and how to think through a problem before writing any code. And now it's the time to get into the actual building blocks of programming itself: data, variables, memory, and data types. So, here what we will cover is these much topics. We will start with the difference between data and information, move into how data actually gets stored and represented inside a computer, and then spend the rest of the video on variables, constants, identifiers, keywords, and data types. And by the end, you will understand exactly what's happening behind the scenes every time you write a single piece of code. So, what is data? So, data is everything we need data for programming as well. Data is a collection of raw, unprocessed facts and figures like numbers, text, symbols. That by itself doesn't yet convey meaning. Data can be numbers, characters, words, images, or sounds. But on its own, data has no context. It just exists. So, take a look at the example 25, 23, 25, 32, 19, 41, 27. So these are just numbers. These are just numbers. Right now they don't mean anything to us. No context, no story. That's exactly what raw data looks like. Then we have information. So if data is raw and meaningless on its own, how does it become useful? That's where information comes. Information is data that has been processed, organized, or given context so that it becomes meaningful and useful. Let's take those same numbers from before and actually do something with them. We start with our data 25, 32, 19, 41, 27. We process it. In this case, by calculating the average and out the other end, we get information. Here average temp equal to 28.8. Suddenly those numbers actually mean something. And what need to remember here is that data becomes information once it's processed and given meaning. Honestly, that's the entire purpose of program, turning raw data into meaningful, useful information. Then data representation. We are going a little deeper here. How does a computer actually represent this data internally? Computers can only store and process binary. So all data, no matter what it is, must be represented as combinations of zeros and ones. A single binary digit, a 0 or a 1, is called a bit, and a group of 8 bits together is called a byte. You can see it right here. 8 boxes, each holding either a 0 or 1, together forming 1 byte. The character A is represented in binary as 0, 1, 0, 0, 0, 0, 0, 1. And that's its ASCII value, which is 65 in decimal. So you might be wondering what is decimal or what is binary. That we will look into deeper when we go for further videos. Just understand decimal is one kind of a number system and binary is another kind of a number system. So every single character, number and symbol you have ever typed gets broken down into patterns just like this ones. Then comes variables, the most important concepts in all of programming. A variable is a named storage location in memory that holds a value, one that can change while the program runs. Like here we can see a labeled box. The label on top, age, is the variable's name and the value inside that, 25, is its current value. So that's the thing a variable makes in the first place. The value inside this box can change while the program is running. Today it might hold 25, tomorrow it might hold 26. The name stays the same, but the value inside can vary. That's why the name variable. Now you understood, I think. So we understood variables, but how actually variables are stored in memory? Where does the variable actually live in memory? So every variable actually lives at a specific location inside the computer's memory or RAM. And behind the scenes, the compiler or interpreter links. I hope you remember about compiler or interpreter. If you are not having any idea, just go back to our previous video and just come back. So the compiler or interpreter links the variable's name to that memory location for us automatically. So in the diagram I have given, we have our variable age and it's actually pointing down into a specific memory cell, address 1002, which is where the value 25 is physically stored. The variable name age is really just a convenient label for us as programmers. In the back side, it actually points to memory location 1002, which stores the value 25. We never have to think about the raw address ourselves. The name handles that for us. So now you got memory address and everything. So how memory address looks inside a computer? Let's zoom in a little more for the memory address concepts and idea. A memory address is a unique numeric identifier that specifies a particular location within the computer's memory. And imagine memory like a huge street of numbered houses. Each house, each byte has its own unique address. Every variable's value is stored at one of these addresses. And thankfully, programming languages let us access our data through the variable's name. So we almost never have to deal with the raw addresses directly. And a memory address is like a house number on a street. The postman, in this case the program, uses that address to find exactly where to deliver or read the data. Then comes constants. Not every value in a program is meant to change. Sometimes we want a value to stay exactly the same throughout the entire program. And that's what a constant is for. A constant is a named storage location whose value cannot change once it has been set. So here we have pi, which is pi, holding the value 3.14159, and it's locked. It cannot be reassigned once it's set. So constants are used for values that should never change during a program's execution. Things like pi, tax rates, or some configuration limits. And using them helps prevent accidental changes while also making your code much easier to understand and maintain. Then literals. So let's talk about literal now, a term you will hear constantly once you start writing real code. A literal is a fixed value written directly into the code, exactly as it should be used. So let's go through a few types. An integer literal like 42 is a whole number. A floating point literal 3.14 is a decimal number. A character literal like A in single quotes is a single character. Then a string literal like hello in double quotes is a sequence of characters. And a Boolean literal like true or false, that is a Boolean literal as well. So the idea to really understand the difference here is a variable can hold a value, but a literal is the value itself written directly into the source code. Hope you understood the difference. Then we have identifiers. We actually name things in our code. An identifier is the name we have given to a variable, constant, function, or other elements in our code. There are some rules to follow when we are giving a name to a particular thing in our program. An identifier must start with a letter or an underscore. It can contain letters, digits, and underscores. It cannot be a reserved keyword. So we discuss what is keyword, that are predefined words in programming language. We should not use those keywords for naming our variables or anything. Then it's case sensitive, meaning age in small letter a and age in capital letter A are actually two completely different identifiers. Okay, just like we name a newborn baby something, but we won't name a baby or a person with numbers except if our father is not Elon Musk. So in that case, we know there are something that we will follow. So let's look at some valid and invalid examples. Here total score and underscore count both are valid, but in the second place it is invalid because it starts with a digit. So it can't be considered as a invalid identifier name. And the total hyphen score is there. Hyphen is not like allowed, because special characters is nothing allowed in identifiers except some underscores only. Okay, hope you understood what is identifier and which are the rules that makes identifiers. Then we have keywords. So sorry to say in the last slide that I said we have previously discussed this. Vaguely we have discussed, now we are discussing deeply. While identifiers are names we choose ourselves, keywords are the opposite. They are the names the language has already claimed for itself. Keywords are reserved words that have a special predefined meaning in a programming language, and they cannot be used as identifiers. So some common examples I have given: if, else, while, for, return, in, float, class. So all these things you have been constantly seeing while writing a programming code or program code. So every single one of these already has a specific job built into the language. Like if we hear food, then we understand it's something to eat. If we hear laptop or computer, we know something it is used for computation or some task to do. What if vice versa? When we hear food, are we thinking about computers? Or else if we are thinking about computer, are we thinking about food in vice versa? It is not happening, right? So similarly, there are some specific words which is already having predefined meaning in the programming languages. So since keywords are reserved by the language itself, you can't name a variable int or if. The compiler would get completely confused about what you actually mean. Then we have data types. A data type tells the compiler or interpreter what kind of value a variable can hold and what operations are valid on it. So why does this matter so much? Well, different kinds of data need different amounts of memory and different rules for processing. Data types help catch errors early, like trying to add a number directly to a piece of text. And they also help the computer use memory efficiently. And a question to consider here is that without data types, what should be the answer for 5 plus apple? It doesn't make sense, right? Data types exist specifically to define which operations actually make sense for which kind of values. Then we have primitive data type. What are the actual basic data types that every language provides? These are called primitive data types. So primitive data types are the most basic built-in data types provided directly by a programming language. As you can see in this diagram, primitive data types branch into four main categories: integer, float, character, and boolean. Almost every programming language builds more complex data structures like arrays or objects on top of these basic primitive types. Everything more advanced you will learn later is ultimately built from these four fundamental building blocks. Then we have integer, floating point, and character data. We are going a little deeper of the primitive data types. Integer is used like this: age equals 25, used for whole numbers with no decimals at all. Then floating point, price equals 19.99, used for numbers that include decimals. And a character, grade equals A, used to store exactly one symbol. Remember, to store exactly one symbol. So when you would actually use each of them, integer is used for counting, indexing, and whole number math. There is no fractional part involved. Floating point is used whenever precision with decimals actually matters. Think prices, measurements, or averages. And character stores exactly one symbol, a letter, a digit, or a punctuation mark, usually written inside single quotes. Then we have another data type, which is Boolean data, which is the fourth and final primitive type. A Boolean is a data type that can hold any one of two values, true or false. That's it. Nothing else is allowed. This data type is actually named after the mathematician George Boole, and it forms the foundation of logic in computing. So Booleans are used constantly for decisions. Things like is 7 is valid or has permission. Like for an example, is raining. When I ask is raining, it's actually true or false. So is raining equals true means that value would then be used later in an if condition to decide exactly what happens next in your program. So simply understand Boolean data is used to define true or false, like on or off conditions. Then we have type conversion. What happens when data needs to move between different types? Starting with the type conversion. Type conversion is changing a value from one data type to another, sometimes done automatically by the language itself. We start with an integer here 5. It goes through automatic conversion and it counts out of the other side as a floating point 5.0. This automatic form is actually called implicit conversion. The language does it for you, usually when it's completely safe to do so. And adding an integer and a float together automatically converts the integer to a float first. So no precision gets lost along the way. Then we have typecasting. Typecasting is explicitly telling the program to convert a value from one data type to another, done manually by the programmer. So we start with a float 9.7 here. We apply an explicit cast using int, which is the keyword used for defining integer data type, and it comes out the other side as an integer 9. Price equals 9.7, then the whole equals int price, and notice whole becomes exactly 9. That decimal portion, the 0.7, is simply gone. Unlike implicit conversion, typecasting is deliberate choice made by the programmer, and because of that it can actually lose information, just like we saw with the decimal part of the number here. So that's about the module 3. We can quickly recap everything we covered in this video. Data is raw facts. Information is data that's been giving meaning and context. Variables are named memory location that stores values which can change. Constants, on the other hand, cannot. Identifiers are the names we choose ourselves. Keywords are reserved words that already had special meaning built into the language. Data types define what kind of value a variable can hold: integer, float, character, a boolean, and boolean are our 4 primitive types. Then finally, the type conversion, which happens automatically, while the another one, typecasting, is done explicitly by the programmer on purpose. So this is our module 3. In the next video, module 4, we are moving on to operators and expressions, where we will actually start doing things with all this data we just learned about. If this video helped these concepts, click for it, drop a like, and I will see you in the next one. Thank you.